So in this video, we're going to look at 5.4, which looks at eigenvectors and linear transformations. So we're going to be looking at how we can incorporate everything that we've learned about eigenvectors and eigenvalues so far and seeing how that relates to linear transformations and change of basis that we looked at in chapter 4. So remember, when you have a linear transformation can always be written in terms of a standard matrix. So we can always find this matrix A such that A multiplied by a vector X is the same as mapping that vector X into a vector space. Okay, so normally we look at T going from Rn to Rm. Okay, so X would be in Rm and then T of X would be in Rm. Okay, so this is what we've looked at before. We stuck with standard bases when we did this, and then we looked at doing a change of basis where we looked at how can we get from a basis B for a vector space to the standard basis, and we use that change of coordinate matrix. Now what we want to look at is when we go from a vector space V to a vector space W, where neither of those have the standard basis. So the vector space B will have some basis B, and the vector space W will have a basis C. And we want to see how we can go between the two. So now we've got this linear transformation that takes the vector space V to the vector space W. Okay, V is an n-dimensional vector space, which means it's going to have n vectors in its basis. So it's going to have basis B, which will be B1. We'll give it an ordered basis B1 through Bn. Okay. Then W is an m-dimensional vector space. Okay, so if it's m-dimensional, it's going to have m vectors in its basis. So it's going to have basis, we'll say C, and that's going to have m vectors, C1 through Cm. Okay. So taking a vector X, which is in V. So we're taking a vector X in V. It can be mapped to W. Okay, because we know that T takes V to W. So X is in V, T of X must be in W. I want to look at X with respect to this basis B. And I want to see where this lies. Okay, going back to what we had here. Okay, we know that V is an n-dimensional vector space with basis B1 through Bn. Okay, so they are our basis vectors. X with respect to B would be our B coordinates of X. So it's the coefficients of these B1 through Bn vectors when I write X as something times B1 plus something times B2, etc. It's those coefficients that will form this B vector for X. Okay? So if that is the case and it's made up of the coefficients of B1 through Bn, that means that X with respect to B must be an n-dimensional vector. It must have n entries in it. So this thing is in Rn because it's going to have n entries because there will be n coordinates with respect to B1 through Bn. In the same way, T of X with respect to C. Now we know that T of X is in W, and we want to write it in terms of this basis, C1 through Cm. Again, T of X with respect to C is going to be my C coordinate vector. Okay, so it's going to be the coefficients of C1 through Cm when I write Tx in terms of those vectors. Therefore, it's going to have m coordinates. It's going to have m entries. So this thing is in Rm. Okay. A good way of seeing where these things map to, just as I've done here, there is a figure on page, let me get this right, page 291. And it's figure 1 on page 291, and it gives you a good picture of looking at where these things map to and from. Okay, so we've done it very algebraically here, but if you would like to see it in a picture, page 291 shows you that. Okay, now what I want to do is to find a relationship between these two vectors. Okay, we already have a relationship between these two vectors. Okay, if you're in terms of a standard basis, you can always find that standard matrix A that will take you from one vector space to another. Okay, and it will represent that linear transformation. But now we're in terms of these different bases. Okay, so the vector space V is in terms of basis B, and vector space W is in terms of basis C. They are not necessarily the standard bases. So we want to see what the relationship between these two vectors is. So I know that X is in V. So that means I can write X in terms of that basis B for V. Okay, I know that I can write X as R1B1 plus R2B2 up to RnBn. Okay, because I know B1 through Bn are my basis vectors for my vector space V. Okay, so I know I can write X in that form. That means that my B coordinate vector for X is just the coefficients of those B's, R1 through Rn. Okay, so I now have a vector for X with respect to B. Now let's look at T of X. Okay, now I know that X is R1B1 through to RnBn. And I know that T is linear. So I can break this up and I can bring those coefficients, those constants, R1 through Rn out the front. So I can write this as R1 T of B1 plus R2 T of B2 up to Rn T of Bn, because I know that T is linear. It's a linear transformation, so I can do that. The other thing that I know is that when I do a change of bases, and we showed this, it was one of the last classes we had before spring break, I know that this mapping where I take X in the standard basis to X in another basis, in terms of another basis, so I take the B coordinate vector of X, this transformation is also linear. And it also turns out that it was 1-to-1 and onto, and we went through a proof of that in class. So I know that this mapping is linear. So what I can now do is say that I want to find T of X, but I want to find its C coordinate. So I want to find T of X with respect to C, which means I want to find this thing with respect to C. So I'm going to do the same type of thing again. I'm going to take what I've just found for T of X. I'll come back a step first. Plus R2 T of B2 plus, in terms of C. And as I said, it is linear. So I can break this thing up and again bring the constants out the front. So this thing can be written as okay. Now, if we look at this, okay, what we have done in each one of these vectors here is we've taken the basis vector B1 within that basis B for V, okay? I've taken B1 and I have mapped it into W. And then I want to find its C coordinates in W, okay? So that means that for each one of these vectors, I am mapping it into W and finding its C coordinates. We already know that each one of those must be in Rn. Okay, so I know that each one of these vectors has m entries in it. And I have n of them. Okay, I have n of these vectors all along. Okay, so all I'm doing is taking each of those basis vectors in B, I'm transforming them to find their image in W, and then I'm finding the C coordinates of their image. Okay, but because each one of those is a vector, I have a vector equation here, and I'm going to rewrite it in terms of a matrix equation. So if you bear with me a second while I write this out, and then you can see how these two things are equivalent. Okay, so what I have done here is I have made a matrix. So this thing here is a matrix, and I'm going to call it M. Okay, it's a matrix M where its columns are made up of these C coordinate vectors of the image of the B coordinate vectors. Okay, so all they are is I've taken each of my basis vectors in B, taken the image and found their C coordinates. And I've put each one of those vectors as a column of the matrix. Okay, and then I have multiplied that matrix by this vector, this column vector, R1 through Rn, which were my coefficients here. Okay, if we look at this, remember when you do matrix multiplication, you do row times column and take the dot product. Okay, so if you do that, you find that you will always get an entry from TB1 with respect to C multiplying R1. You would get every entry from TB2 with respect to C would multiply R2, etc. So you would actually come out with this equation that we have up here, but we now just have it in matrix form. As I said, I'm going to call that matrix M, and this thing over here, this vector, you should notice from what we did on the previous slide, this thing was just my x vector, but it's B coordinates. So this is just x with respect to B. So what we have done here is we have written the C coordinate vector of T of x and made it equal to a matrix times the B coordinate vector of x. That is exactly what we wanted. We have related these two things here, x with respect to B and T of x with respect to C. So we know that T of x with respect to C is that matrix M multiplied with the vector x, but taking its B coordinates, so it's x with respect to B. And that matrix M is just where I have taken each of my coordinate vectors in B, so the basis for the vector space that I start in, the basis for that domain vector space, okay? I'm going to take each of its basis vectors, I'm going to map them into W and then find its C coordinates in W. And that matrix that I get will transform the B coordinates of x to the C coordinates of the image of x. That matrix M has a name. We call it M is the matrix for T relative to the bases B and C. Okay. Kind of a long name, but that's what we tend to call it. So what this matrix M does, it acts like that linear transformation, and it acts like that standard matrix that we have for a linear transformation. But now what it does is it takes us from one basis for a particular vector space to this other random basis for a particular vector space. Okay, so we are not going from Rn to Rm anymore. We are going from one random vector space to another random vector space, and we may not have standard bases for these two vector spaces. So it will take us from whatever basis we want for one vector space to whatever basis we want for the other vector space. Okay, and it's done by that matrix M. So it's slightly more complicated, but it is just an extension of that standard matrix that we've looked at before. Okay, I'm going to do a quick example of this. This is a very simple example and a very small example. So we're going to let a basis B be the basis for a vector space V, and D, again, is going to be a very small basis, D1 and D2, be a basis for W. So we've got two vector spaces, both are two-dimensional. Then I'm going to take this linear transformation that's going to take V to W, okay, such that I'm going to define two operations on this. So T of B1 is actually going to be 2 of D1 minus 3 of D2. And then T of B2 is going to be negative 4 of D1 plus 5 of D2. So we see where those basis vectors in B, so the basis for V, we're going to see where those basis vectors map to in W, okay? And we've got those written in terms of those basis vectors in W. So we want to find the matrix for T relative to B and D. Okay, so that matrix M, okay, it's relative to B and D, where I go from V with that basis B to W that has the basis D. So M, I'm going to take each of my basis vectors in B and I'm going to write them in terms of my basis D. Okay. Now, T of B1, okay, we said was 2D1 minus 3D2. Okay. The coefficients of my basis vectors in D in this will form the coordinates with respect to D. So in this case, T of B1 with respect to the basis D is just 2 of D1 minus 3 of D2. That's my coordinate vector with respect to D. Then T of B2 with respect to D is just negative 4 and 5. So they are my D coordinate vectors for the images of both B1 and B2, okay? The D coordinates of the image of B1 was 2, negative 3, as we knew that it was 2D1 minus 3D2. And my D coordinates of the image of B2, well, we knew that the image of B2 was negative 4D1 plus 5D2. So those coordinates were negative 4 and 5. Okay, so it's very similar to what we've done before with change of basis. It's just taking it a step further. A common case that we come across quite a lot is actually where you're mapping to the same vector space. So you're mapping from one vector space to itself. So we go from V to V, and we're going to stay within the same basis. So we're not going to change basis when we do this transformation. We're going to stick to that same basis for V. So we keep the same basis. So when we map using T, we're going to keep to that same basis for V the whole time. Okay. Because of that, because we don't change basis, if we come back to what we actually had in our definition for the matrix M, okay, what we did was we took each of our basis vectors for V, We transformed them to see where that image was in W, okay, in which case we're still looking within the same vector space here, because remember what we're looking at now, we go from V to V, okay? So that would mean that T of the basis vector would still land in that vector space V, and then I want to find its coordinates with respect to the basis that I started in, okay? So if I do that, I'm sticking to the same basis in both times because I want to stick to the same vector space and the same basis. So we actually call M the matrix for T relative to just B. Or shorthand, we actually call it the B matrix for T. And we denote it as this. So before we denoted it as M when we were going from one vector space with a certain basis to another vector space with a certain basis. But now because we are keeping to the same vector space and the same basis, we're actually going to denote M by this T with respect to B, the B matrix for T. Going back to that formula that we had before. So from before, what we had was T of X with respect to that basis C for W was that matrix M multiplied by the B coordinates of the vector X. But now what we will have, okay, we will again want the B coordinates of the image of X because X is in V. We now know that T of X is also in V because we're mapping into V. And I'm keeping to the same basis. So I still want the B coordinates of the image is equal to this matrix M. Actually, I'm going to rewrite that in terms of what I've just said. Oh. There we go. Okay. I'm going to write that matrix M as my B matrix for T multiplied by the B coordinates of X. Okay. The question is, what is this matrix? What does it look like? Let's start on a new page. Okay. Thinking about what M looked like. Okay. I took the image of each of my basis vectors for the basis of the vector space I started out in, so in V. Okay. So I take each of those basis vectors. I find the image of it. And then I found the B or C coordinates, depending on the basis for the codomain, okay? I then wrote this in terms of that basis. So I found, before I found its C coordinates, because that was the basis, C was the basis for W. So now, B is my basis for my codomain V, okay? So I'm going to find the image of my basis vectors, and then I'm going to find the B coordinates of that image. Okay, so I'm staying within the same basis. Okay. There are a couple of examples of this. I found another example online that I quite like, which involves matrices and finding out how matrices map between one another. That is on page 3 of the notes for today. I actually really like the example in the textbook, and it's kind of close to one that you'll do for your homework. So I'm actually going to go through that example. It's example 2 on page 292. So there is another example in the notes if you would like to go through that later on as well. But I'm going to stick to the example in the textbook for now. So we're going to have this linear mapping that is going to take the polynomials of at most degree 2 to that same space. Okay, it's a linear transformation such that if I take a polynomial in P2, so this is a generic polynomial in P2, it's going to map to A1 plus 2A2 times T. Okay, what you may notice here is this is actually the derivative mapping. Okay. But we're going to see if we can find the B matrix for this transformation. And I'm going to make my basis B for P2 1t and t squared. Okay, so I'm actually going to use the standard basis for P2 here, but it will work whichever basis you used. Okay, so I want to find that B matrix. Let's write this out first. Okay, I know I've got 3 entries in my basis. I've got 3 elements to my basis. So this is going to be t of B1 with respect to B, t of B2 with respect to B, and t of B3 with respect to B. And I need to find each of these where B1 is going to be 1, B2 is going to be t, and B2 is going to be t squared. And then we're going to find the images of them under this mapping and then find their B coordinates. So let's start by finding t of 1. So t of 1. So when we have 1, that means A0 here is equal to 1. A1 must be 0 and A2 must be 0. So that would map to A1 being 0 and A2 being 0. So t of 1, the image of 1 is just 0. Then let's move on to our next basis vector, our next element, which is t. So t of t, so that would make A0, 0, A1 is 1, and A2 is 0. So that would just map to 1. And then t of t squared. So that would make A0 would be 0, A1 would be 0, and A2 would be 1. So that would map to 2t. And that's exactly what we expect. If this linear map is the derivative map, each one of these takes the derivative of each of those basis elements. So this is what we get. Now we need to write this in terms of our basis. So we need the B coordinate vectors. So let's first do t of 1 with respect to B. Let's find its vector. So this is just 0. Okay. So with respect to our basis, okay, 0 would equal 0 times 1 plus 0 times t plus 0 times t squared. That would make this vector, just these coefficients of our basis vectors. So 0, 0, and 0. Okay. Then let's move on to the coordinate vector for the image of t. So again, we know that t of t is just 1. So I need to write 1 in terms of 1t and t squared. Well, we know that 1 is equal to 1 times 1 plus 0 times t plus 0 times t squared. So this vector is just going to be 1, 0, 0, and 1, 0, and 0. And finally, we want t of t squared with respect to b and find its coordinate vector. Well, t of t squared was 2 times t. So again, let's write 2t in terms of our basis elements. So that's going to be 0 times 1 plus 2 times t plus 0 times t squared. So that makes our coordinate vector 0, 2, 0. So putting it all together, that would give the B matrix for t as 0, 0, 0, 1, 0, 0, 0, 2, 0. Okay. So what this matrix is going to do, let's relate this back to the problem. What this matrix is going to do is for any polynomial p, okay, what this will do, if we write that polynomial p in terms of our basis, so we're going to find the b coordinate vector for the polynomial. So in this case, our basis b was 1t and t squared. So I'm going to write my polynomial in terms of that standard basis, 1t and t squared. And what this is going to do is it's going to take that vector multiplying it by that matrix is going to tell us where the image of that polynomial gets mapped to with relation to our basis b. So it's going to map it to the image of p in relation to the basis b. So we can then find the coordinate vector here. It will be the coordinate vector, and it will tell us how many 1s, how many t's, and how many t squareds we have in the image of p by mapping it through t. Okay, so that's what this matrix does. Okay, as I said, there is another example in the notes on page 3 if you would like to look at another example. The next thing that I want to look at is relating this back to eigenvectors and eigenvalues that we have looked at throughout chapter 5. So normally when we are dealing with a linear transformation, just going way back to when we started looking at linear transformations, we can write it in terms of a standard matrix A. Okay, and if we are going in this case from Rn straight to Rn, so we're keeping within the same space, that would make A an n by n matrix. Okay, if you're mapping to Rm, then it would be an m by n, but right now we're just going to keep within Rn. Okay, that makes A a square matrix. Now, we know from previous chapters, okay, from 5.2 and 5.3, that if A is square, if we can find eigenvalues and eigenvectors such that even if I've got an eigenvalue that has a multiplicity of 2 or above, as long as the associated eigenspace has the same dimensional basis as the multiplicity of that eigenvalue, I can decompose A, okay, and I can say that A is equal to P, D, P inverse. So as long as the eigenspaces that are of the eigenvectors, the eigenspaces, their dimension is the same as the multiplicity of the associated eigenvalue, that means that I can diagonalize a matrix, okay? So when we did this and we decomposed it into P, D, P inverse, if you remember, D is a diagonal matrix, and on the diagonal you have the eigenvalues. Okay, and then P was made up of the basis vectors in the eigenspace. So it's made up of eigenvectors that are associated with the eigenvalues in D. Okay, and we also said that those eigenvectors are linearly independent. Okay, and we have n of them. So we have n linearly independent vectors, each one of which has n entries. So therefore, they must form an eigenvector basis for Rn. So that's what we looked at last time. So there is a basis, we'll call it B for Rn, that is made up of eigenvalues, or eigenvectors, sorry, for A. Okay. It then turns out that if A were this matrix that represented the transformation T, it actually turns out that D is going to be the B matrix for T. Okay, so if T of x is equal to A times x, where A would take us from Rn to Rn, what D is going to do is instead, when we use the eigenvector basis for Rn instead of the standard basis, D is what is going to take us from the vector in terms of that basis B into the image of that vector in terms of that same eigenvector basis. Okay, so this is going to be called the diagonal matrix representation theorem. Okay, so we're going to suppose that A is equal to P, D, P inverse, where D is diagonal. So we are assuming here that A is diagonalizable, which means that it has eigenvalues. They may be repeated, but the eigenspaces associated with each eigenvalue has the same dimension as the multiplicity of the eigenvalue. So we know that this thing is diagonalizable and is similar to a diagonal matrix. Now, if B is a basis for Rn, formed from the columns of P, so formed from the columns of P, which are the eigenvectors of A, then D is the B matrix for the transformation. So it's just T with respect to B. So if T can be represented by the standard matrix A, such that T goes from Rn to Rn, what A does is it takes a vector that is in the standard basis for Rn and then it maps it to its image that is in Rn, again in the standard basis. What the B matrix for T is going to do is it's going to map the vector x that is in terms of the eigenvector basis B. So we're going to find the B coordinates of that vector x, so in terms of the basis of eigenvectors for Rn. And this matrix D is actually going to map it to the image of that vector, again in terms of that eigenvector basis. So it's going to give us the B coordinates of the image of x. Okay, let's do a quick proof for this. So we're going to say that P is going to be B1 through Bn. So each of the B vectors is a column in P. So the basis B is just B1 through Bn. So we're just making P to be the matrix of the eigenvectors. Okay. Now, we know from what we've done in the past with change of coordinate matrices that P is just the change of coordinate matrix that takes us from x in terms of the basis B, and it's going to map it to x in terms of the standard basis. Okay? So by multiplying by P, where P is just made up of the basis vectors, you can think of each of these basis vectors as being written in terms of the standard basis. Okay, so you can have B1 with respect to the standard basis. Think of it in that way if you want to. But P is just PB that we've looked at before with a change of coordinate matrix. So we know that P is a change of coordinate matrix, so we can also rewrite this like this. So we know that each of those basis vectors must be linearly independent. The eigenvectors we know are linearly independent from the last chapter, and we know that therefore if it's got linearly independent columns and it's a square matrix, it's invertible. Okay, I'm going to use this fact in a second, but we know that T of x is just A times x, okay, where x is in Rn and T of x is also in Rn. We're staying within Rn. Okay, I want to look at the B matrix for T. Okay, and as we've always said before, okay, the B matrix for T, I'm going to take the image of each of those vectors in B, and then I'm going to find its B coordinate vector. And I'm going to do that for every single one of those eigenvectors that is in that eigenvector basis for Rn. And I'm going to map it, and then I'm going to find its B coordinates. Okay. Now, from this definition up here, okay, T of x is equal to A times x, I can rewrite each of these images, T of B1, I can write that as A multiplied by B1 and finding its B coordinates. And up to A times Bn and finding its B coordinates. Okay. Now, coming up to this definition here, okay, I know that A times a vector is going to be another vector, okay? I've got an n by n matrix multiplying an n-dimensional vector, okay? So this is just going to be another vector with n entries in it. So I know that if I have a vector, okay, I can rewrite x with respect to b as P inverse times that vector. So each one of these columns I can rewrite as P inverse times A times B1. Then the next column would be P inverse A times B2, etc. all the way along to P inverse A times Bn. Okay. Now, I have two matrices, P inverse and A, in every single column of that matrix. So I'm going to factor them out. So that's going to give me P inverse A, and then I'm left with my columns as B1 through Bn. Well, that is just the matrix P. So this thing is P inverse AP. But we said A is P, D, P inverse, okay? By definition of how we set up A and how we set up P and D, okay? Because we said that P was made up of the eigenvectors of A, and we're assuming that A is diagonalizable here, okay? We are assuming here that it's going to be similar to a diagonal matrix just because of how we set P up, okay? Wouldn't necessarily have to be diagonal, as we'll talk about in a minute, but that's where we're heading with this, okay? We're saying that A is going to be diagonalizable, okay, with how we've set this up. So therefore, as this is the case, I can rearrange this to say that D is P inverse AP. So therefore, this must equal D. So that means that the matrix that was similar to A, which in this case was that diagonal vector, that diagonal matrix with the eigenvalues in it, that is my B matrix for T. Okay. And that's the end of that proof. Okay, let's do a quick example that looks at this. So let's define T that goes from R squared to R squared as T of X is equal to A times X. And I'm going to say that A is 6, -1, 2, 3. Now I want to find a basis, call it B, for R squared, with the property that the B matrix for T is diagonal. Okay. Now, the big thing that we have to remember here is that the matrix that we want for T, okay, the B matrix for T, has to be diagonal. That tells us that we are looking for the matrix that is similar to A that is diagonal. That means that we must be looking for the eigenvector basis B, okay? As we'll look at in a second, you don't necessarily need to have the diagonal matrix that is similar to the matrix A in order to find a basis such that you would get some form of basis where you can find another B matrix, okay? In this case, because we are saying that it must be diagonal, okay, whenever you see that, you know that you are looking for the eigenvector basis, because then you know that the matrix that is similar to A would be D, that diagonal matrix that is made up of the eigenvalues, okay? So we know that that is our formula. We know that the columns in P are the eigenvectors. They form an eigenvector basis for Rn, in this case R2. And we know that D is similar to A. And D is the B matrix for T, okay? So what this basically amounts to is finding the eigenvectors and eigenvalues for that matrix, okay? Now, we actually did this previously in 5.2. I actually found the eigenvectors and eigenvalues of this matrix. and we actually decomposed it into P, D, P inverse. And we actually found that 6, negative 1, 2, 3 was equal to 1, 1, 2, 1, 4, 0, 0, 5, and then the inverse of P. Okay, so that's what we found before. So therefore, if we use this basis for Rn, this would make the B matrix for T to be this diagonal matrix. Okay, so as long as we use this basis instead of the standard basis, we know that our B matrix for T that will take us from a vector X in terms of B to the image of X in terms of B is this matrix here. Okay, so whenever you see one of these where they want the B matrix to be diagonal, make sure you are looking for eigenvectors and eigenvalues and looking for that decomposition. Now, as I said, when we went through this proof, okay, we were assuming here that we were going to take P to be this matrix made up of eigenvectors, and therefore we could find D that is similar to A, and D was made up of the eigenvalues, and we knew that it was diagonal. But we didn't actually use anywhere in here the fact that we needed that eigenvector eigenvalue decomposition, that PDB P inverse, okay? We didn't actually say that it had to be that way. What you can actually do instead is if you take just some matrix C that is similar to A, which means that I can make A to be some invertible matrix P such that A is P, C, P inverse, then A is similar to C. So as long as I can find this matrix P that is invertible such that P, C, P inverse is A, then I know that A and C are similar. The proof still holds for this. It just means that my B matrix for T may not be diagonal. Okay, it may be some random matrix that is just similar to A. But all this proof actually showed you, okay, was that P was made up of the basis vectors. We were doing, for our example, we were just saying, we'll set that to be the eigenvector basis. If you don't necessarily need it to be the eigenvector basis, but just some basis for Rn, okay, you can then get out some matrix C that is similar to A such that it's the B matrix for T. Okay, so coming back to here, okay, if I set some basis B and I'll call them B1 through Bn again, be a basis for Rn. Now, it can be any basis whatsoever, however you decide to find that basis, as long as it's n linearly independent vectors that span the whole space, you're good to go, okay? And you're going to make P equal to the matrix that is made up with those basis vectors as columns, okay? Then the matrix C that is similar to A then becomes your B matrix for T by that same proof as before, but you are just using a random basis for Rn in this case. Okay, there is a figure, let me get this right, I think it's figure 5 that you will be looking at. Yes, figure 5 on page 294 will show you how all this stuff kind of multiplies together, and it's actually a very good diagram if you would like to look at that. But all this means is that the B matrix of the transformation is just a matrix that has to be similar to A. It doesn't necessarily have to be diagonal unless that is what the question is asking for, is for that B matrix of T to be diagonal, in which case you know you're looking for that eigenvector, eigenvalue decomposition, okay? But right now, all you have to know is that the B matrix for T is just similar to A, such that A is the standard matrix for T, okay? So the B matrix of the transformation is just the matrix C that is similar to T. Well, that is similar to A, sorry. Okay. Where T of X is equal to A times X. Okay. This is normally used when you have a case where A is not diagonalizable. That's normally where this comes into play. So if you end up with, you're trying to figure out the eigenvector, eigenvalue decompositions, and you're trying to figure out, okay, here are my eigenvalues. I've got some eigenvalues that are repeated. Let's say you had an eigenvalue that occurred 3 times. Okay, so it had multiplicity 3. But you then found out that the associated eigenspace only had 2 vectors in it. So the multiplicity of the eigenvalue did not equal the dimension of the eigenspace. Therefore, it's not diagonalizable. That is when this would be used. Okay. There is a good example 4 on page 294. Let's have a look at this and we can do this together. Okay. So it says that we're going to take A to equal 4, 4, -9, -8. Okay. And then my basis vectors, B, are going to be 3, 2, and 2, 1. Okay. That's my basis for R2 here. Okay. Now, the eigenvalue, lambda equals -2, okay, has multiplicity 2, but a one-dimensional eigenspace. So there is only one vector that is in the basis for the eigenspace that is associated with lambda is equal to -2. So we know that A is not diagonalizable. We cannot write it as P, D, P inverse with a diagonal matrix D. So what we want to do here is we want to find that matrix that is similar to A such that it's going to be the B matrix of T. So it's going to be the matrix that is going to map any vector X in terms of our basis B into the image of that vector in terms of the basis B. Okay, so we want to find, we'll call it C, which is the B matrix of T. Okay, now we know that A and C have to be similar. So we know that A is equal to P, C, P inverse. Okay, now P is made up of, the columns of it are just the vectors that are in the basis B. So P is 3, 2, 2, 1. And I want to find C. Well, we know that P is an invertible matrix. Okay, we know that it's made up of basis vectors, hence its columns are linearly independent. It's a square matrix, hence it's invertible. So I now know, as A is PC P inverse, that tells me that C, if you want to play around with this, multiply both sides on the left by P inverse and both sides on the right by P. That will give you P inverse AP. So if I want to find this matrix C, all I have to do is do P inverse multiplied by A multiplied by P. So C is equal to P inverse AP, which comes out to -2, 1, 0, -2. Okay. This particular matrix, where we've done this transformation, is actually called the Jordan form of A, and it has the eigenvalues on the diagonal. Okay, we're going to talk more about these types of matrices later on, but the thing that I want you to take away from this example is that your B matrix for T, if A is diagonalizable, where A is the standard matrix for T, then that B matrix for T can be made up of that matrix D, where D is the diagonal matrix made up with the eigenvalues on that diagonal. Okay, So we could take that eigenvector eigenvalue decomposition, and we could just say that the B matrix for T is that matrix D where A is PD P inverse. But sometimes a matrix A is not diagonalizable. But from our proof, we know that any matrix that is similar to A can be written as the B matrix of T, okay? As long as it's similar, and we're going to make that matrix P the matrix that is made up of the basis vectors, okay? And then that matrix C will be the B matrix for T. Okay, that's what I want you to take away from this example. If you've got any questions about this, please let me know. I know it's not the easiest chapter in the world, and it may take a few goes to try and figure out what's going on, and maybe a few practice problems. This will be in some problems that I will give you as practice for the tests, and make sure that you go through those. But as always, if you've got any questions, let me know, and I will see you in the next video.